So welcome everybody, and thank you for joining us today for this International Solar Energy Society webinar. We are looking forward to all of your participation and questions in the Q&A session later. My name is Joanna Costello, working at the headquarters of the International Solar Energy Society in Freiburg in Germany, and I'm going to give you a short introduction about what ISIS is and stands for. The International Solar Energy Society is a non-profit, UN-accredited membership NGO. The ISIS vision is to achieve 100% renewable energy for all, used efficiently and wisely. We represent a diverse membership of academics, researchers, energy practitioners, consultants, students, businesses and advocates. ISIS works together with like-minded organizations from countries around the world to advance the renewable energy transformation. By becoming a member of the International Solar Energy Society, you are supporting the 100% renewable energy movement. The presentations and recording of this webinar will be available for 24 hours on the ISIS website. After that time, we will post them to the ISIS members area. If you are an ISIS member, which I see many of you who have registered for this webinar are today, please simply log into your account and then click on the members area icon on the top level menu, and you will already see the library of past webinars. If you are not a member yet, please visit our membership page, and we really do encourage you to sign up. That's join.ises.org. You are welcome and encouraged to ask questions at any time throughout the webinar. To ask a question, select the questions pane on your screen and type in your question. Please specify who your question is directed to. Questions will be addressed after all the presentations in a Q&A session. So we would also like to encourage you to use the ISIS discussion forum on LinkedIn to continue the Q&A and the discussion even after the webinar has ended. Before I hand over to our moderator for the webinar, I would like to thank our sponsor, Murdoch University, the host of the World Renewable Energy Congress 2017, for your support. Dr. David Goodfield, the Congress Manager for the event, is online today for this webinar and will say a few words about the event happening in February at Murdoch University before the Q&A session. So through sponsorships such as these, donations and also the support of ISIS members, we can continue hosting these free webinars for you. For more information about becoming a member or sponsor, please visit our website www.ises.org or get in touch with us by email. Our moderator for this webinar is Peter Ray, the President of the World Wind Energy Association since 2015, which is a partner in the International Renewable Energy Alliance. Peter has been the honorary chairman of the Alliance since it was formed in 2004 and has brought together the International Hydropower Association, the International Solar Energy Society, the International Geothermal Association, and the World Bioenergy Association. He was also chairman of Hydro Tasmania, is a lawyer by profession, and a former senator in the Australian Parliament. We are very honoured to have you here with us today, Peter, and the floor is now yours.
Very much, and a warm welcome to all of those who are connected to this webinar, 100% renewable energy for islands. And perhaps it's as well to note that the world is full of islands, many of which, if not all, nearly all, have been powered by diesel, if they've had power at all. With their electricity power plants, their motor vehicles, desalination if they have it, and the like. Many of these are in the Pacific, and if they're to have renewable energy, then the lessons which can be learned out of the experiences of our speakers today will be particularly valuable. In discussing islands, however, I think it's important to just remember that there are islands of a different sort on many of the areas of the developing world where there are villages and isolated areas which have similar problems to the problems of islands. I'd like to congratulate ISIS on organising a series of webinars, including this one, which Joanna has done such an excellent job in preparing. As part of the REN Alliance, which has taken up the cause of 100% renewables, it's very appropriate that we're having people who have something to significantly offer in relation to 100% renewable. And I think there are lessons which can be learned from the islands which will then transfer through to achieving the overall 100% renewables. The alliance was formed in 2004 with a view to working together to ensure that all of the possible ways of cooperation could achieve a rollover to renewables. And the target of 100% has now been adopted, and since Paris last year, when 195 nations of the world agreed to pursue a very strict program of moving towards a rollover to renewables, I think you can say that the movement to renewables is really with us. The rate of rollover, I think, can be seen from the fact that the remarkable figures published by REN 21 following the first IREC in Bonn in 2004. And wind has grown from 59 gigawatts in 2004-05 through to 433 at the end of 2015. That's a very significant increase, but even greater has been the increase in solar. And I'll just use these as two examples. Solar was 5.1 gigawatts in 2004-05 and has increased to 227 gigawatts at the end of 2015. That's some indication of the immense rate of growth which has taken place. Last year alone, solar added 50 gigawatts, 10 times the original total in 2004. More has been invested in new renewable energy in the past 2 or 3 years in each of them than has been invested in fossil fuel and nuclear. That's another indication of the extent to which the rollover is taking place. In effect, we have great advances in relation to storage. We've got better technology in relation to generation. We've got better technology and improving technology in relation to management. You'll hear some of the details of those improvements that have been able to be identified in relation to islands from our speakers, who will be including, the first one will be Simon Gamble. Simon is a leader in the field. He's been involved for Hydro Tasmania, which is Australia's largest renewable energy generator. He's been involved with a specialisation in the development of the work that he'll describe on King Island and more recently in relation to Flinders Island, two of the islands for which Hydro Tasmania is responsible and which are well clear of being able to be connected by to the Tasmanian grid, so they have needed to have special work done to develop, if possible, 100% renewables on those islands. It's a remarkable development that's taken place since we first put some wind, 3 small wind generators on King Island in 1995. The work on that started, and in 20 years there's been a remarkable development which he'll describe. But as well, we have the benefit of Simon Franklin, who has particular experience in relation to islands and will tell about some of the studies conducted in relation to Pacific Islands, particularly Tuvalu and Tokelau. Then we'll move on to hear from Jeff Stapleton, and Jeff has a long history of involvement, but particularly in the work with REAP and the Pacific Islands. and REAP has undertaken a program in relation to the Pacific Islands, and Jeff has been involved and will tell us about that. And then finally, as Joanna mentioned, we'll hear from David Goodfield. So we have a program which we're about to start, which I believe will help everybody to understand what the opportunities are and what some of the work has produced in relation to research and development towards 100% renewable energy for islands. Simon Gamble, would you like to commence?
Thank you, Peter. What I would like to talk about as part of today's webinar is to describe a journey that Hydro Tasmania has taken in the management of the two island systems that Peter has alluded to, and to show you the steps that we've taken now over close to 2 decades to transition these islands to be able to operate today at 100% renewable energy penetration. Now, Peter has given some background as to who Hydro Tasmania is and the responsibility that we have for the islands of King and Flinders in the Bass Strait. I'm just having some difficulty in forwarding my slide. Oh, there we go. So yes, we are the utility responsible for power generation, distribution and retail to all of the communities on these islands. And it's our involvement in those islands that's given us the important understanding of the high costs of those systems, and in particular how renewable energy can be utilised to reduce the operating costs associated with these very remote and logistically challenging locations. And we've now moved to a point where we are a developer and owner and operator of other systems. So we're essentially taken these lessons and are now exporting these to different parts of the world, both as an advisor and as a builder of these hybrid systems. So fundamentally, I guess, just to put the setting in everyone's mind about where renewable energy has a role to play in island systems, is to start with where the asset has come from. And traditionally, power generation in these remote locations has been based on diesel, and it's for good reason, in that those diesel generation sources are very secure and reliable, and they're reasonably simple to operate. So it made sense at that point in time to use that technology. But of course, because of their location and the logistical challenges and the price of the fuel, that represents a very high cost supply option. If you look at the pie chart on the right-hand side, you can see that essentially, if we look at the composition of costs, diesel can be as high as 90 to 95% of those costs. So it's the fuel that is very costly, and it's the fuel that we're able to displace through the use of renewable energy technologies. And by doing so, we're able to reduce that levelized cost of energy. That's what LCOE stands for. By investing in upfront capital, we're displacing the ongoing operational costs of the diesel fuel, so we can transition to a lower cost environment. But doing so, it can be complex and can introduce significant reliability issues. And so we have to be very aware of these, and in particular recognise that with adding renewables, we're actually displacing the diesel generation that we've relied upon to maintain that reliable power supply. So what we need to do is look at replacing that diesel technology with non-fossil fuel burning technologies that can support the network and support the reliable supply of power. And there are a range of options available, and I'll go through a lot of those today. So when taking this transition to a renewable future, we need to do a considerable amount of planning and thinking about the steps that are needed to be taken, and in particular to be wary of over-investment and underutilising the assets that we put in to get the best value out of those, and make sure that we always have an eye to how that system is going to be operated. Is it going to be reliable? Is it mature? Does it offer viable operation and maintenance practices, given that these technologies are being put into very remote areas? So what I'd like to do really is talk a lot about the King Island case study. And now King Island is located in Bass Strait, in between the mainland of Australia and Tasmania, as I hope you can see from this figure. And it's largely a rural community, very low population of about 1,600 people, but quite a high load as a result of the industrial use on the island, which includes cheese making and meat facilities, so meat production. And it's also quite geographically large and involves a lot of distributed network of high voltage equipment, and that's one of the important aspects of these renewable systems is, can you operate, not only supply the power, but can you operate the network safely and efficiently? So as Peter said, we took the first steps back in the mid-90s and finally commissioned and opened the first project, our first renewables project in 1998. And as you'll see, I'll take you through these examples and I'll show you in idealistic terms the sorts of issues that we uncovered and the challenges that we overcame as we added this renewable content. So on the bottom right hand side you'll see a figure there showing the yellow curve, which is essentially what an idealized solar system would do at a very low level of penetration, and the red line indicates the impact on the existing diesel system, and these are the two interactions that are very important to consider. So back in 1998, when we added this first wind farm, we essentially introduced a small amount of renewable energy, and we limited the amount of that energy that was added to the system through just installing those first 3 small wind turbines, and that had no impact on our operations. We essentially saw that as a reduction in load in the system, and that's what that figure on the bottom right hand side is indicating. So you can see that the diesel engines and the power system really just responds very adequately and normally by reducing its output, and essentially that allows the renewable energy to be served directly to customers. And that saves diesel immediately, and it's really the low-hanging fruit that's available to these systems, and we saved 15% of diesel in doing so. A few years later, we expanded our wind farm on King Island. It's got a fantastic wind resource, so it is the most cost-effective renewable generation supply to look at. But at this point, we installed, had 2.45 megawatts of renewables. And if you compare that to our minimum load, which was only 1.2 megawatts, you can see that automatically you're going to have an issue, and that we have more renewable generation supply than we actually have customers' load to serve. And so we have to control and limit the production that comes from that renewable system at this point. And really the figure on the bottom right hand side indicates why that is. And essentially what it means is, what it's showing is that we have to clip the renewable generation so that when we ask our diesel generators to cover the remaining load, we don't push them down too low in their generation output. Diesel engines can only really reduce their production to a certain level of about 30% of their rated capacity. So we have to protect those engines, we have to make sure they're operating over a normal range, and to do that we obviously have to limit the amount of renewable energy that's put into the system. So it means we maintain that reliability, which is all important, but of course it also means that there is more diesel displacement that we could achieve if we had a better mechanism, a better way of integrating that renewable energy. But still at this point you can see we had a 30% reduction in our diesel fuel use, which is fantastic. Later in our development cycle we recognised that if we used an enabling technology, it would allow us to better utilise that renewable energy that we were previously curtailing. What we introduced was what was called a dynamic resistor, or just a load bank, an artificial load, which absorbs that excess renewable energy that we were previously curtailing. So it was energy that wasn't being produced that we allowed to be produced and absorbed by the load bank. And that seems pretty counterintuitive as to why that would benefit the system. But essentially, as you can see through that idealised graph, we're introducing that load, we're allowing the renewables to contribute their maximum output, but the distinction is that the load is something that we can control very accurately and very quickly. And by controlling that load, we're actually obtaining what's called an ancillary service, some useful service out of that renewable energy generation. And in this case, we're using that to do what's called frequency control. So it's actually controlling the frequency of the entire island system, and that's a job that's normally done by the diesel engines. So what we've done is we've transferred a job from the diesel engines and we've given that to the renewables. And by doing that, we're actually saving some further diesel consumption. So it's, and it also protects those diesels from going into that reverse power mode that I mentioned earlier. So we've introduced the first enabling technology, and we're getting a further diesel reduction through greater renewables contribution. So at this point, we're still needing to have those diesel engines operating, and predominantly that's because we don't have any other source of generation in the system that could cover the loss of renewables. Renewables, as we appreciate, are variable in their production. We could have a loss in wind, we could have a loss in solar through cloud cover. So we need, if we're going to take the next step, we need to get to a point where we can take all of the diesels offline and essentially allow renewables to contribute all of the power to the system. And as of 2014, we were able to achieve this using a flywheel technology. So we had the renewable capacity, and we had a fully automated system, but what we required was a piece of equipment that could provide a range of other ancillary services. And in this case, we needed to control voltage in the network. We needed to add inertia so that we essentially could slow down any of the disturbances to the power quality through the variability of the renewables. And very importantly, we need to have what's called firm capacity, the ability to provide power instantaneously to support the network if we lost wind or solar. And so we installed this particular system for the first time in the world, and essentially the renewables are used to drive the big blue flywheel that you can see there. It's 4 tons of steel, and that rotates at high speed, and it means that we have available at all times a generation unit that can inject power. There is a diesel engine associated with it, but that's only used to start the wheel spinning, and then that goes offline, and then is only really called on if that system needs to inject power for a lengthy period of time before we can stabilise the network with other diesels that we can bring on if we lose wind or solar for a sustained period. So at this point in our path, in our development path, we're able to achieve 100% renewables, but we're not able to sustain it for very long if we lose wind or solar. So one of the other options available to developers is to use technologies such as energy storage. As you can see from the idealized graph there, we're absorbing that renewable energy and we're storing it in a battery, but what that allows us to do subsequently is to deplete the energy storage in the battery system, which saves diesel fuel further into the future. So there is a little bit of load shifting in terms of shifting renewable energy from one period and recovering it at a later period. And I don't want to get too technical, but there are a lot of other things that a battery can do as well, and that includes provide some of that frequency control services by changing its output very quickly from injecting power to absorbing power, and it's also there and available and online to us if we do have a shortfall, so we can tap into it to provide that system security that I mentioned previously. So quickly, some other things that we did. One of the challenges with island systems, as with all power systems, is to manage the balance between demand and supply. And all of the things I've just talked about have been in the supply space. Of course, one of the other options, if you're trying to balance demand and supply, is to alter your demand. And so we also rolled out a smart grid system which incorporated real-time aggregated load control. What that means is we could essentially alter the demand of our customers so that if we had a shortfall in power generation, because, for example, the renewables were diminished for a short period of time, rather than increasing output through artificial purposes like the battery, or worse, having to switch on diesel engines, we could actually reduce the load in our customer base by turning off hot water systems, other pumps and things like that, loads like that could be interrupted. And we did a range of other things as well, like electric vehicle charging, so we could ensure that we weren't charging electric vehicles unless they were using renewable energy. And of course, because we have this technology installed, it means we have the very live and real-time information. We can actually provide that back to our customers, and we do so via a smartphone app. So as a customer, you can see what your energy consumption is, not once a quarter, but in fact for the last hour, and you can also see what your solar and your electric vehicle consumption has been in the previous 24-hour period. Having done all of this work in renewables, one of the other things to recognise is that an alternative, if you can't displace further mineral diesel, is to replace that with a sustainable fuel source. And so we did a lot of work around the use of biodiesel and came up with the facility you can see there, where we essentially have a dedicated biodiesel system, and we can blend biodiesel into our existing mineral diesel stocks depending on the seasonality of available supplies of biodiesel. So we did a lot of tests on that and showed that that was perfectly reliable and safe for the diesel engines to operate on that fuel source. So what we ended up with was this system that you see here on this figure. It's a very integrated system. It's all coordinated by an automatic, fully autonomous control system, and it needs to be, because the decisions and the actions that are taken to ensure power quality is maintained are done in the order of milliseconds. And so this has been in for a number of years now. We've now had well over 3,000 hours of 100% renewable operation, and we in fact have better system performance, better reliability, and of course we've lowered our costs. We're saving more than $2 million a year in fuel consumption. One of the figures I have to show you is this figure here, which outlines a particular day, and if you look at this figure, you'll see how the systems interplay with each other. So the green line in this case is our wind, and you can see it's highly variable, and in this case it was fluctuating around the customer demand for the day, which is the grey line. And so what you can see there through the different colours, the orange there is the battery and its performance, and you can see it's very fine resolution of injection and absorption of power, and it's doing that very rapidly to maintain the balance of demand and supply, and it's controlling frequency as it does that. And you'll note there's quite a significant absence of red, and that's our diesel production. So we actually only operated diesel engines for 4 hours during this particular day, and in fact we've had periods of 61 hours continuously without switching on our diesel engine. So these systems can run for days on end depending on the availability of renewables. So it's highly effective. Just very quickly touch on a couple of other case studies. Flinders Island is a system that we also have responsibility for. Slightly smaller population, again very rural, but still dominated by really good wind resource. What we are doing on Flinders Island is we want to take our lessons from King Island, which involved us doing a lot of construction activity at the power station. One of the things with islands is obviously they're very remote and logistics are quite difficult, and the availability of very skilled labour is one of the issues that needs to be sort of resolved, and taking a lot of skilled labour into these environments can be very difficult and costly. So what we are doing is moving from the design that you see on the left, which is everything built on site construction activity, to the diagram on the right, which is more what we call a scalable modular system of equipment that's built, manufactured off-site and tested off-site, and then is brought into the remote location. It's all of the enabling equipment that I've mentioned. It's the flywheels, it's the battery banks, and the dynamic resistors, and of course the control systems that need to come along to integrate renewables into a power system. And what we're currently doing is we've installed a system, a modular scalable system that you can see in this photo, which is taken from our Flinders Island site, and we've currently got engineers on site that are connecting and commissioning this system. So as far as installation goes, that complete system that you see there was installed in less than 2 days. So it takes what we did on King Island, which took closer to 18 months to construct on site, to have all of that work done off-site and then brought and installed in a very quick time on island, which of course brings the costs of these systems down further. Another quick case study is a project we're doing on Remoteness Island in Western Australia. And this particular project is more of a tourist island, so there's very few residents that live permanently on the island, but there are close to 600,000 visitors that come to this island annually. It's a fantastic place to go and visit. And traditionally, again, they've relied on diesel fuel for power generation. They also have a unique requirement for water purification services and water treatment. And so the aspect of this project that I think is quite interesting is the fact that it's combining the lower, more cost-effective way of producing energy through renewables, but also bringing a reduction in costs to water services. So essentially we're using renewable energy to reduce the cost of supplying clean drinkable water. Now the really interesting aspect of this is we're using the desalination plant which exists on the island as one of the forms of demand management. So we're controlling the desalination to better match the available renewable production. That lifts the penetration of renewables and reduces the diesel fuel that's used in that system. So we're looking to achieve a 45% renewable contribution on Remoteness, and as you can see there, the project's well underway, but is going to be finished in about March next year. So we're doing work on site just at the moment. And lastly, we are working on a very interesting project in outback South Australia, which is for the township of Cooper Pedy. Now this is, as Peter mentioned, this is one of these islands of sand rather than of sea, in that it's a remote community, it's disconnected from the large grids, and it's a very unique environment in that it's hot and dry rather than salty and humid, but it does have available renewables in the form of excellent solar and surprisingly a very good wind resource. So what we're doing here is working with the developer of this project to install all of the enabling systems that I've mentioned, and we'll be manufacturing those off-site and bringing those into the Cooper Pedy environment and basically acting to commission and make sure the system is operational and able to provide the objective of a 70% reduction in diesel fuel through the use of 4 megawatts of wind and 1 megawatt of solar. So that's a really innovative project as well. Now, my last slide is really just to invite people to go to our website if they want to see one of these projects working in real time. You can see that at our King Island Renewable Energy Integration Project website. And if you have an iPhone, you can download our smartphone app as well, which shows you the performance of these systems in real time. And that's where I'll leave it today. So thank you.
Thank you very much, Simon Campbell, for that very interesting presentation. I'm going to quickly move on because we're a little bit short on time to our next presenter, and that is Simon Franklin from IT Power Australia. So the floor is now yours.
Thank you very much, Joanna, and thank you to Peter as well and all the other speakers. It's an honour to be able to present today. Look, what I want to talk about today is again, it's going to be sticking with the theme of 100% renewables, but it'll be moving to a slightly smaller example than what Simon's just spoken about there, and moving to a different geographic location. So we're going to move into the Pacific now and talk to you a little bit about Tuvalu. So just I'll run through this slide quite quickly because I do understand we're pushed for time. Just to give you a little bit of a background on IT Power, we're a global company headquartered in the UK with offices throughout the world, and we've been in the renewable energy consulting game for about 35 years. And what that means is because renewables 35 years ago were not on large grids, they weren't a major thing. A lot of the technology was going into very remote communities and also to small grids. So we've got a real expertise around what we call islanded grids, be they on a physical island or just islanded from a main grid. So as I said, the example I'd like to run through today is of Tuvalu, which is in the Pacific Ocean. You can see right here on that top image exactly where it is. It's sort of almost directly north of New Zealand. And the islands I'm going to focus on within Tuvalu are the top 3 islands on that bottom map, which are Nanumanga, Nanumea and Nuatau, and also Vaitupu, which is just north of the main island with the box around it, Funafuti. So some background on the islands is they're all very, very small coral atolls with very little landmass available. There's only approximately 10,000 people living across all the islands, and the bulk of those are based in Funafuti. So the populations on the other islands are very low. And what this means is it adds a lot of challenges and difficulties to all sorts of things, and particularly delivery of energy and electricity. So the only way to get in to Funafuti is there's two flights a week coming out of Fiji, and then from there, if you want to travel to one of the northern islands, one of those three at the top, it's about a 24-hour boat ride, and they usually only run every 3 to 6 weeks. So this can create some fairly serious risks when it comes to fuel supply to those northern islands, and they often run without power simply because they've run out of diesel to generate the electricity. So the current grids there, as I've mentioned, you probably picked up on, they're all diesel-based grids. They're all low-voltage AC grids, meeting very small loads. They've been in place since about 2001. Prior to that, there was no grid electricity available on the islands. All the electricity throughout the islands is delivered by the Tuvalu Electricity Corporation, which is headquartered back in Funafuti, the main island, and they have technicians that will make trips out to the islands as needed, and also have local operators who are in charge of the power stations. And that photo on the right there is another sort of key reason why we're pushing towards renewable energy in these islands and replacing the existing fuel supply. Those barrels that are sitting there, old diesel barrels, that's as far as they go. They're never going to go back to be recycled. It's far too costly to actually take the empty barrels off the island. So they end up just sitting in stockpiles or getting thrown in the lagoon, which is really, disappointing result for the local environment. So these two photos will show you an example of what the power station looks like. It's not quite as high tech as what we might have seen from some of Simon's slides previously, but is very typical of a lot of the remote islands throughout the Pacific. At least we've got 2 generators there that both look like they're close to it in working order, which is not necessarily the case in a lot of these islands. And if there is ever a problem with these generators, it can take a significant amount of time to actually get parts to repair them. And while generators there are available to meet the load, there's often one of those which is out of service because it's needing to be maintained. So I've picked up on some of the issues already around power delivery on the islands, and these issues are what's been the driving force behind this project to take the islands to 100% renewable energy. And these key issues are mainly around the reliability of the system. So typically there'd be approximately 12 to 18 hours worth of electricity available per day, but this can fall dramatically down to as low as 2 hours a day when those fuel shipments don't come in. And that would typically be because there may be a problem with the ships. They may be needing to go for maintenance, or if a storm blows in and the seas get large, then they simply can't travel, and the people on the islands have to do without electricity. There's also issues with the diesels breaking down and things of that nature, as I mentioned previously. It's also incredibly costly to deliver power on these islands. I mean, diesel electricity is not cheap at the best of times, but when you've got to bring it in single barrels and in very small quantities to very remote areas, the cost increases significantly. So we're probably looking at a delivered cost of energy up to about $1.50 per kilowatt hour. And this is really not sustainable. So the government subsidises this cost of energy quite significantly, and the local tariffs on the islands are around about 25 cents. And this means that there's quite a drain on the government funds to be able to maintain the power supply to these communities. So this here is quite a typical example of how equipment is brought into these islands, and it outlines another challenge of actually providing decent electrical services and any projects on the islands. So you can see in this picture here there's a cut coming into the reef, and that's the only way that you can bring equipment into the island is through that gap. And you need to use quite small boats to get the equipment in. So the next shot here is showing just how you need to take much larger loads of equipment and break them down and put them onto the smaller boats to bring them in. And then there's often very little equipment on the island to actually transport that, the goods around for installation. The islands are also very vulnerable to poor weather. So the shots that are up on the screen now show just some of the devastation that can result from large storm events. And events like this seriously damage the local environment, make it very hard for people. And on top of this, they can't get additional equipment or goods in because a lot of the concrete that's been undermined there, you can see it's been cut away in that bottom right-hand picture, that actually ends up getting pulled back off the island and is usually deposited back in that cut in the reef, and then you can't get supplies back into the island. And when you're reliant on food, fresh water, and diesel for power supply, that can be an issue. So part of the design of this system was about having something that would give reliable power even after emergency events like this. So the aims of the project that was implemented here, and it was a New Zealand government funded project that was aiming for 100% renewable energy supply on the 4 islands, and also to increase the availability of electricity up to 100 for 24 hours of power per day. All the components and the systems were designed to last for at least 20 years. There was allowance for some replacement of key components where necessary, and also to reduce the operating costs for the local government to try and make the systems more sustainable. As part of the project, we undertook a scoping mission to outline what the loads were on the island. You can see here that they're very, very low loads. We've got a peak of only about 30 kilowatts rather. And there's also the bottom line in that chart demonstrates that there's actually not a lot of data available. It's very poorly monitored on these islands. So the sections in red there are actually areas that we've had to sort of guess at what the usage might be and fill in the gaps because the data is just simply not available to build a profile of the island. We've allowed for some load growth on the island, which is typical of when you provide better energy services. People tend to go out and buy new products, and that increases the demand. So the average usage is about 550 kilowatt hours a day. We've allowed, as I said, for load growth, and that's things like people, once they have reliable electricity, will typically add things like fridges and freezers, which weren't viable previously because they would continuously go through a freeze defrost cycle when they didn't have consistent electricity. There's also a significant jump in electricity use during particular times of the year as people who may be based off the islands come home for special events such as Christmas. So keeping that in mind, the system that was designed is predominantly a solar and battery system, but also has a backup diesel that is able to cope with these increased demand events and also provide power when there's been poor weather for a long period of time. Now the system that was deployed there was based on the SMA Sunny Island architecture, which is an AC coupled system. It's two generators that have been kept, one at 60 kVA and one at 100. There's about 33,000 amp hours of batteries in the system, very large storage system. It was built a couple of years ago now, so it's still incorporating lead acid batteries. These systems, as they move forward, they'll probably look at new technologies of batteries, and that will probably further reduce the cost of these systems. Approximately 200 kilowatts of solar required. Some of the key considerations and features of the design were that it had to be modular because there's very little access to technicians on the island or skilled labour. If a component fails, you need to make sure that you can continue to deliver power effectively while you're getting that component replaced. There's significant corrosion risks on the island, as there is anywhere in the Pacific. Anyone who hasn't been out there just can't understand how quickly things will degrade and corrode in that environment. So all of the structures and all of the equipment needs to be designed with that in mind. Also very prone to cyclones coming through, as you would have seen in those previous shots. It can be quite damaging, so a significant amount of effort needs to be done around the footings of the PV array and the power station structures. And also need to be a requirement for things like minimising parasitic loads such as air conditioning. So this is a system that ended up going in. You can see a shot of the array from above. You can see how little land area is available there. We're sort of squeezed between the ocean on one side and an internal part of the lagoon on the other side. There really is one of the major challenges on these projects is finding suitable land availability. In some cases it's simply not there, and you actually have to build the PV array much higher and effectively use the land underneath as well, because you can't afford to lose that land. You can see the masses of batteries that have gone in, sealed lead acid batteries in the top right of that shot in the powerhouse. And picking up on my comment about the modular design, you can see in the bottom left all the inverters that have come in, and that means that there's less risk around failure of any single component. And the power station has been built with this solar passive design, so significant ventilation into that building. Overall, the system's performed really well so far. It's oversized for the current load, which is exactly what we'd wanted. It's reduced the cost of operating, so it's reduced the cost down to about 55 cents a kilowatt hour. This is including an allowance for replacement, but does not include repaying the initial capital for the system. Also, quite a lot of effort went into training the local operators for this. It's a new system for them. It's quite difficult to operate, so there needed to be a lot of capacity building undertaken, and that included getting as many local operators to be involved in the construction of the system, also the commissioning and troubleshooting, and then also providing some of the operators back in Funafuti, the capital, with additional training so they can go and troubleshoot any of the trickier problems. And ultimately, the driver behind this project is for the community, and there's been an outstanding response from the community. They're really, really wrapped in the project and really excited to have access to modern, high-quality electricity supply. So finally, just just some of the lessons that have come out of the project, and I'll wrap this up quite quickly because I know we're going over time. One of the risks we see with these systems is they actually become too reliable, and what that means is the operators stop maintaining the generators because they don't need to run them regularly, and they become complacent. And what happens is then when they do need to be called on, they're not available, and this can actually lead to problems with the system or over discharge of the batteries. Some potential social problems around a community adjusting to having 24-hour power, and then the other lessons are picked up on earlier around getting access to data and the logistics being very, very difficult. But I might leave it there, so thank you very much.
Thank you very much as well for that excellent presentation. I'd also like to remind the audience that you can type in your questions that you have for the panelist speakers in the questions pane, and we'll try to get to them during the Q&A or by typing in the answers. Our next speaker is Jeff Stapleton, who I'd also like to say a special thank you to for helping get this webinar together with Monica Oliphant. Thank you for the organization of this webinar. Jeff is an ISIS board member and also one of the co-founders of the Global Sustainable Energy Solutions, GSES. So Jeff, the floor is now yours.
And you'll just confirm you're seeing my screen?
Yes, we do.
Thank you. Yes, good afternoon or good morning, depending on which part of the world you're in. Thank you for attending this seminar. So the first two speakers, they actually spoke about real projects actually happening and actually looked at different sizes of projects. Both those sizes is what's going to be needed in the Pacific Islands over the next many years. There's a map of the Pacific Islands. You get a copy, you can download and have a look at this presentation and study it clearly. There is 26 countries or territories spread across the Pacific Ocean that are considered as part of the Pacific Island nations. But the interesting statistic, and Simon Franklin touched on the issues of getting to some of these spots. It covers 32% of the Earth's total area. A whole world's landmass can actually fit into the Pacific Ocean. So when you're talking remoteness, we are now talking that some of these islands are extremely remote, no roads, only by boats, and as Simon mentioned, many times weeks apart, or in some cases only once every 6 months. So we are talking extreme difficulties, but spread across that the area is the population, so we'll show soon. The data that I'm going to be showing in this presentation is all taken from a document that was prepared by New Zealand MFAT and European Commission for a summit that was held in Auckland in June this year. The website's linked, so the next few slides, the data has been taken from that document, so if you want to find out more about each of these countries and what are they doing, you can have a download and have a read of that document. But that is what we're talking about, an area as big as the whole world's landmass, but only with a population of just over 11 million people. So it beggars to have to think about the logistics of how to provide people services. Take Papua New Guinea out of the mix, you could see that's over 8 million of that 11 million people. So you've got just over 3 million people scattered over a very, very large area where people are looking for services. The idea of this presentation is to actually give you an overview of what these countries are aiming to do in their heading towards 100% renewable, some of them. So I'll give a brief overview of the different countries. Cook Islands, you've got one main island, Rarotonga, another very popular tourist island north of it called Aitutaki. So they both have grids on them, and then they have the northern group and the southern group. So they have a very ambitious target of heading towards 100% renewable by 2020. That, when some countries immediately, when you say 100% renewables, they just immediately think of grid-only electricity. That is not the situation here in the Pacific. 100% renewables is being met by diesel grids at the moment, but then putting the PV, wind, hydro into those grids, or in some cases being met by the mini grids as seen in Simon Franklin's presentation, or in even some instances just simply solar home systems go onto individual houses. Federated states, there's 4 states, 4 main islands in each state, but then numerous small islands scattered around. You can read their targets. Fiji, 2 main islands, large islands. Fiji is blessed with a lot of hydro, which Cook's and FSM does not have. And then they do also have a number of small islands. Kiribati, 2 major islands, as well as then numerous smaller islands. However, to even travel between the main island and then to an island called Christmas Island, you actually got to pass through another country. There's not even a direct flight internally. Marshall Islands, about 20 inhabited atolls. You've pretty well got 50% of the population lives on a diesel grid, and the rest is actually being supplied by 120 watt to 150 watt solar home systems individually on each house, and they actually have 2 technicians on each atoll to service those systems. Nauru, 1 main island. Niue, 1 main island. Palau, a scattering of islands. Papua New Guinea is the big one. Now you'll see its main target is to have access. It only has about 12% of its population of 8 million people currently with access to electricity. So they are providing some of that by renewables, but its greater focus is to actually get electricity to those countries. Samoa has a target of aiming for 100% renewable electricity generation by the end of next year. Samoa has the advantage of being a mountain, 2 main islands, 6,000 feet in the middle, so they have hydro access. Cook Islands, with its 100% renewable energy target, doesn't have hydro access. So over the years, it'll be interesting to see how both meet their 100% renewable energy targets. Solomon Islands is another island with a lot of unelectrified people, but it does have the 20% target from renewables. You can scatter around. Tokelau actually was the first country to go with 100% renewables a number of years ago. Its loads did increase, so it has got a small amount of fuel usage, and that's its target now, is to get rid of that fuel usage. Tonga has the main island, the middle island group of the Hapai, then the northern island group, Tuvalu, which we just talked about, and Vanuatu. So in each of the documents, that document I referred to, there's a couple of pages on each country. I've just taken a couple of the countries just to show what's in there. So you can, if you want to have a look, download. And it also then talks about the types of projects. So at the Cook Islands, 8 PV diesel hybrid systems to cover the 6 Northern Island group. More and more solar, but interestingly, you would see there's 2 megawatts of privately owned PV on the main island. And this is happening on some of the major islands in the Pacific. People are putting in private PV. You then do have the Southern Island group, and they are now getting their diesel hybrid systems. So with their 100% renewable energy goal, it is also consistent of those diesel hybrid systems going in. Samoa, it's increased since 2013 from 7.5 megawatts to 15.4 megawatts. It has total generation, you can see there, of 69. That's total generation, because they all have many, many spare diesel generators because of the remoteness. and it has 100% access to main islands, and the small island between the two main islands has their own solar power system. So the current set of things, they'll have 50% generation, and they're aiming for that 100% by the end of next year. Tonga, I'll leave that to read for the sake of time. So there are two associations in the Pacific who are working with the governments and the utilities to help them achieve their aim. Pacific Power Association is the association of all the utilities, and then there's the Sustainable Energy Industries Association. These two associations work basically together. PPA more with the utilities, SYAPI with the industry, but all technical guidelines, technician certification program has all been set up to be supporting the projects that are going to meet these 100% renewable energy targets for the countries. And parallel at this point of time is also an EU-funded technical education, where in 15 of the countries we're working on common curriculums, building the capacity in technical colleges to have the manpower in the future to be able to service the systems once they're in. Yes, there's plenty of sunshine in the Pacific, but this is the issues as they get to these high penetrations that they've got to overcome. It's the cloud cover issue. When it's on a big land mass, that can be spread out, but when it's on a small island, the effect of the cloud cover can be catastrophic and can sort of lead to having to have diesels as spinning reserves, and hence why more storage will be needed. Just to finish off, it's just again showing similar photos what you saw with Simon, but as you can see, there are some countries where there is no gap in the roof. The boat's got to park outside, they've got to transport it in, and then they've literally got to walk over the reef carrying the equipment in. And then sometimes at high tide they can come in onto some of the islands over the reef. But as Simon pointed out, there are a lot of issues with trying to get products to these remote locations. So I thank you for your time and attending the webinar. Thank you.
Thank you very much also. Now I've just shared my screen. It might take a minute or two to come up, and I'd like to introduce Dr. David Goodfield, who's going to say a few words about the upcoming Congress, the World Renewable Energy Congress 2017.
Thank you, Joanna. Yeah, thank you to the Society for the opportunity to sponsor this event, and it's been an extremely interesting insight into renewable energy technology implementation and integration, has it not? I'm here to commend Murdoch University for putting on the World Renewable Energy Congress in February next year, so see the date on the left please, and our sponsors and supporters underneath. But I particularly want you to embed the website in your minds please at the bottom in blue, so that you can log on to our website and get some more information about the Congress. You will see that in the green block above, a very important date there, 30th September, wherein abstracts have been extended to. So please give it some thought now. You've got 5 weeks, so all of you listeners, perhaps do come to sunny Perth in February next year. Next slide please. Next please, Joanna. Yes, now you'll see on the left there a long list of topics that we've included in the conference. You can see there's a wide variety there, from biofuels and waste to energy to policy matters surrounding renewable energy integration, very topical from South Australia here at present, building science, sustainability, material science to some extent, large extent storage is on the books there, with urban development, with smart grids and obviously renewable energy in all its forms, PV and wind, and solar thermal and wave technology even from our local Carnegie group. You'll see there a list of eminent speakers, quite a variety of areas they come from. Particularly I want to point out there Dr. David Renee, who is president of ICES and also of the Global Solar Council, which came out of Paris last year. I can point to an enormous variety there on the right of invited speakers. Now, if you'd like to go back to the previous slide, thank you. The variety that we present we will have presentations at the conference is backed up by a number of field trips on the built environment, renewable energy systems and storage, and the like, and green buildings, biomass, and geothermal. But you've seen from Simon Gamble that Remoteness Island, which is 22 k's off the coast here, we're going for our technical tour to finish as a social tour at the end of that technical tour on the island. And we hope that that will encourage you to come to Perth. Bring your swimming costume with you. So please refer to the website, have a good look at it, and if you can make the trip, if you're overseas or wherever you are, please do, and we welcome you with open arms. It'll be a very interesting and valuable conference. Look forward to seeing you all. Thank you.
Thank you very much as well, David, for sponsoring this webinar. Great. I'd like to now move on to our questions and answers session. So you've all been very active already in typing in your questions for the panelist speakers. The panelist speakers, if you also like, you can respond by typing. But I'm also going to read out a few of the interesting questions that were sent to us, and you can all unmute your microphones and we can start discussing these questions. So the first question I'd like to read out, which reflects a lot of them that have come in, and it's to Hydro Tasmania. And it is the question, what are the key challenges in upscaling the systems demonstrated on King Island?
Okay, thank you, Joanna, for that question. Essentially, we've designed, King Island is what we'd call a megawatt class system. It's already operating at about 3 megawatts, and we have two challenges at that scale, and that is to downscale the system so that it's useful for the many thousands of islands that may be in the a few hundred kilowatt maximum demand, and then we have the challenge of upscaling it to the larger grid systems, say the Australian grid. I guess the way we've addressed the downscaling is through the modular system, and we now have particular those technologies that I've mentioned. We can produce those at a scale from 500 kilowatts up to several megawatts as individual units, and then to upscale that further we just use multiple systems. So for example, with battery systems today, they come in a form that's pretty scalable in that they're largely containerized, and so you can bring in more energy content through bringing in more 20-foot or 40-foot container systems, and there are several examples of those now in the tens of megawatts. And of course, by connecting them at strategic locations in the grid, you can either support a local area of network or combine their action to support the entire network. So yeah, with our flywheels, again, we're using two flywheel systems at Cooper Pedy, but we're only using one on Flinders Island, and that just shows you how we sort of scale the technology to get that larger. So I hope that starts to address that sort of question.
Thank you. I'm going to read out another question addressed to Simon Franklin. Says, thank you for your presentation, and why did you install the resistor load on Flinders Island? doesn't the energy storage / batteries provide the auxiliary services and make the resistors redundant?
I think that might be actually for Simon Gamble.
Okay, sorry.
Okay. Yes, it is quite confusing to think about the interaction between the different systems. I guess the thing to remember with the load bank is that it's available all the time, 24/7. With an energy storage system, you have a state of charge that you need to manage. You have to be very mindful of your energy storage being either full and not able to accept any further load. So in essence, you can't charge your battery once it reaches a certain state of charge, especially when you're talking about absorbing a lot of power. So that really limits its usefulness and its availability. So a load bank, however, it has maximums and minimums, but essentially you can run that system all day and it can never reach its full capacity. So that's one of the aspects. Another is that the load bank is a very cheap piece of technology, and battery systems are far more expensive. And so if you can get a significant amount of usefulness out of the load bank, then it could be, and in many cases we've just put in a load bank and not put in a battery, so it could be the best technology to provide that particular service that you need, which is controlling the frequency of the system. And it may not be worth installing a battery system, because if you don't have enough surplus, it doesn't necessarily make it economic to store the excess for a later period of time. So I'll probably leave it there, I think.
Okay, thank you. Then I have another question for Simon Franklin. You've answered this one by typing as well, but maybe you can elaborate a little bit more on it about your consideration of other technologies such as swimming PV structures, or also wind turbines, considering given the limited land area available. So a question really about how do you pick which renewable technologies fit best?
Yeah, no, that's a really good question. In the case of the Northern Islands of Tuvalu, there was sufficient land area available to use standard PV structures, and so they offered the most economic solution. However, we're currently working on a project in Funafuti, which is the main island, which is very limited in its land availability, and we are considering floating PV structures there because it's probably looking like the best choice. We did consider wind as well. There's a very poor wind resource on these islands, and there's also some significant challenges around the continuing operations and maintenance of wind turbines. We've seen quite a number of examples of failed wind projects in the Pacific because the operation and maintenance requirements are not met, and that leads to breakdown of the turbines, whereas there's very little operation and maintenance required for PV systems.
Okay, thank you. We have another question which I'll read out. Will 100% renewable energy for Tuvalu solve their climate change issues that they are currently facing?
No. Not by any stretch of the imagination. I think it will take a much greater input from the rest of the world to have any impact on the climate change issues they're facing. One thing, interestingly enough, to notice though is one of the islands we were working on as part of this project in the last extreme weather event was actually completely inundated. So the entire island was underwater. So climate change is a real risk for these islands.
Yeah, yeah. Another question on Tuvalu is what is the total cost of the system on the island of Tuvalu? So do you have any figures for costs?
I believe that the cost across the 4 islands, and each system was slightly different in size, was approximately 15 million, I think.
Okay, thank you. We have a question here for Jeff Stapleton. Given the small size of some of these specific communities that you described and the variability of solar on small islands, what is the best mitigation for this? Batteries, diesel, flywheel for larger systems? So that's a question for Jeff Stapleton.
to a certain extent, all of the above, depending on the actual application. Because for the very small systems, there will be batteries. So, and then as the penetration gets higher, people are hoping as the battery storage prices decreases, that will be the leveler. Spinning reserve of diesel will have to keep on being used for the cloud cover in some situations, and they'll only be overcome by the use of batteries. Flywheels, they do have their own inherent using up energy just by keeping them spinning. So that itself could be a problem on some of these. And also the issue that Simon Franklin addressed is such a high salt in that content and corrosion issues on anything that's spinning could cause a problem down the track. So they have been looked at, but to my knowledge at this point in time, flywheel technology hasn't been applied to any of the islands in the Pacific. There's also that thing of trying to keep things simple to technologies they're also familiar with at this point in time.
Okay. Here we have a question for Simon Franklin. Was there a particular type of frames that were used for the solar farm on the island, given the corrosive environment, and what sort of a lifetime is expected of the solar farm in that environment?
Yeah, so there weren't special module frames used. The modules themselves are adequately protected, but the array frames were anodized aluminium, so they needed to be, most aluminium frames are not anodized, but we required at least 25 microns of anodization on all the frames that were out there, and also stainless steel fixings were used to try and prevent some of this corrosion. What we've seen is that solution tends to have the best lifetime, and we expect at least a 25-year lifetime out of this. What we've seen in other systems where galvanized steel has been used, for example, there's significant corrosion even within a couple of years.
Mm-hmm. Okay, and I have a question here which any one of the panelists can feel free to answer, and it's about tidal energy, and was that considered in any of the projects? Is there potential there for islands to use tidal energy?
I can add something there. We have had both wave and tidal proponents looking at the King and Flinders Island facilities. So King Island has an excellent wave resource, and Flinders Island has a very good tidal resource through a chain of islands there. There's a significant tidal flow that's observed. And so, yes, the technologies themselves are pretty immature, but developing quite rapidly in some areas. There are some Australian technologies that are being demonstrated at scale, and essentially what we've done at both of our locations in King and Flinders is ensure that we've got somewhere for those systems to connect, and then would need to integrate them with the existing power systems, and hopefully that would then further increase the renewable generation. But of course, the correlation of those generation sources needs to be looked at with, for example, the existing technologies. It's not going to add a significant value having, for example, wave, if that wave corresponds to when we also have a significant wind available. So those are other sort of challenges to be met.
Mm-hmm. Thank you. Here's another question from somebody asking that, or stating that they saw that one of the examples was a private system on one of the islands, and are many of these projects commercially viable without government support or subsidies?
It's Jeff here, I'll answer that. In places like Fiji, systems up to 200 kilowatts have been installed on some of the tourist islands. The people running those islands have a high fuel bill, and so there are a number of systems going in with no funding or no government subsidy at all. That is also happening in some of the islands with grid connected systems, where there are a couple of, one firm in particular who actually installs the system on the roof of industrial sites and sells the solar electricity to them. So what is happening in larger countries is starting to happen commercially in some of the larger Pacific Islands. So there is private sales of systems occurring.
Thank you. I have a few questions here about electric vehicles and also sustainable aviation. If this was at all considered into the plans for renewable energy on the islands for transport and also for tourism.
Yeah, look, I can jump in first, and I'm sure that Simon Gamble's probably got a comment on this as well. We have considered electric vehicles for a number of the islands that we've been working in recently. So we recently undertook a large study for the World Bank in Tonga, and also the study we're doing at the moment in Funafuti is looking at ways to shift from other uses of fossil fuels out of that are not within the electricity sector. So it is something that we're actively considering.
And I can add to that. I was just typing in an answer to that question. We've obviously we put in the infrastructure on King Island to do smart EV charging, and we really did that as a demonstration aspect. It's not of sufficient scale to make a considerable impact into the sort of renewable electrification of transportation, but the potential is certainly there. And you know, we were looking for project partners from electric vehicle companies to come forward, but we haven't been able to attract anything at this point. But we have all of the infrastructure in place to do that. You know, but that's only one way. It's only charging, smart charging. It would be fantastic to incorporate the ability to have vehicles connected to the grid and to utilise the distributed storage that they would have on their fleet. And yeah, so I guess one thing to say here is that islands present an excellent opportunity to do these sort of high penetration studies and to get some really early insights into how that might affect the bigger grids into the future. You know, for example, if we had as few as 20 vehicles on King Island, we would see a significant impact, and we'd be able to, you know, forecast that to a much larger system.
Thank you. Just to expand on that question as well, do you think there's a demand or a plan to export the King Island model internationally, so for other islands?
Yes, we're quite active in that at the moment. We've had a lot of engagement with the utilities across the Pacific. Many of those countries that Jeff mentioned, we've engaged with them. We've had a number of visits from islands, representatives from the Marshalls and Fiji, Samoa, the Cook Islands have come to see us, and we host events annually on these islands. We have another event coming up towards the end of the year in late November, and that's called Island Power System Connect, and it's really targeting utilities that want to come and visit these island facilities and get some first-hand experience in how to own and operate hybrid systems. It's, you know, if you have the training, these not that challenging. You can of course build capacity within the utilities to be able to operate such systems. So we think it has great potential because they've got very high cost environments, and renewables with the right enabling equipment and with the right mature technologies makes a lot of sense.
Thank you. A question for all the panelists about the introduction of these different renewable energies and smart grid systems. Did this act in any way to encroach on the personal lifestyle choices of the islanders in terms of energy consumption, or do you think this was all very successful and there was no negative opinions or a public backlash or anything about this on the islands?
Maybe I'll jump in first on that, and then the others can have a go. What we've seen is quite a positive response the projects, there has been some, I suppose, misinformation about the projects. It's led to a little bit of pushback, and that's mostly around people believe once a renewable energy system goes in that the electricity that comes out is free. There's this conception within the community that because the fuel is free in terms of the sunshine or the wind, that the power must be free as well. And they're then concerned when they don't see a decrease in the cost of their electricity tariffs. So that's probably the main backlash we've seen. Hasn't been, in terms of people's attitudes and usage of electricity, obviously there's a significant growth in the remote islands where we're working. That can lead to some potential social problems, which I did outline in my talk around people using electricity at different times of the day and potentially disrupting their neighbours, but that's very rare.
And I could add to that, both of those issues. We on our King and Flinders Islands, we have a very high cost operating environment, but the state government has put in place a subsidy for power. So power is actually supplied at a cost that is below the cost of generation. So in essence, the customers are already receiving a subsidy. So when we went ahead with our renewable projects, again, we had to work with the community in understanding that whilst we were reducing the cost of supply, we weren't able to reduce the price offered to customers because essentially we were offsetting that subsidy that was being provided already by the state government. So there was that aspect. Another aspect is we actually formed a community consultative committee as part of our project and worked with that community over many years so that they could be engaged with the project. And one of the reasons we did that was because we had to roll out equipment to individual customers at the residence, and we needed to engage with volunteers that wanted to be part of our project. And so that committee was really our avenue to engage at the local community level, and they were our representatives as part of this project. And what we found was that we had a really high level of support. We had an oversubscription to our smart grid project. We had more people volunteering than we could have had equipment that we could install. And then when we've had engagement through things like project open days, people have flooded us with interest. In fact, we've had we had an open day. We had close to half of the island population turn up on that day for a visit. So there's a lot of interest and support.
Just the one thing I'll add, just as a different looking at it. We also do need to remember there are a lot of people in the Pacific who still do not have any access to electricity. In the outer islands of Vanuatu, particularly Papua New Guinea. So if anything, you have those people who are sort of saying, when are they going to get something? And they're not going to get grid because that's not going to be viable for some of these remote villages. And there are still solar home system type projects being implemented by some of the donors where people still have their individual solar home system.
Great, thank you very much for those answers, and that was the last question I'm taking because we are out of time, unfortunately. I'm going to hand over to Peter Ray once more to give some final words, and then I'll explain a little bit more about our survey that we launch at the end.
Well, thank you very much to all of the speakers who have given us a wonderfully clear and encouraging view of what are the needs, the challenges, the opportunities, the potential solutions for the islands of both sorts. And in talking of islands, just to explain to people something of Tasmania and its two islands, which we've heard quite a lot about. Tasmania is an island itself about the size, slightly smaller than the Czech Republic, about the size of Sri Lanka, and has about now for many years almost 100% hydro, wind and solar. So there's a lot of experience there, and this has encouraged the development about which Simon Gamble has spoken so well. It's encouraging to know, I think, that there are opportunities for the achievement of the 100% renewables for the islands, but there's obviously considerable work still to be done to achieve that, with the problems which have been outlined by both Simon Franklin and by Jeff Stapleton. It's not an easy task to accommodate the needs of many of the very small islands and some of the larger islands, but working together, I'm sure that we of the world of renewable energy can bring solutions and bring achievement which will enable the achieving of 100% renewables for the islands of the Pacific. And thank you very much to the sponsors, Murdoch University, and a final very warm and strong thank you to Joanna and to ISIS for putting on this webinar, which has been, I think, I could summarise by saying, an extremely interesting exposition of the subject of 100% renewables for the islands. Thank you.
Yeah.
Thank you. Thank you very much, Peter. And thank you to all our panelist speakers for sharing your knowledge and expertise with us today. And Peter, for your opening and closing statements. David Goodfield for your sponsoring of the webinar. And I hope that we have a lot of interest in your conference in Murdoch University in February. It was a very, very inspiring session, and I hope you all enjoyed it too. To contact the panelist speakers for further information, please see their own contact information in their presentations, which are all available to download from the ISIS website. I have that link in the questions window for all the audience participants. If you use social media, we encourage you to connect with us to continue the discussion and continue to stay tuned to renewables on islands. Last but not least, thank you to our audience for joining us today. We look forward to welcoming you at another ISIS webinar. Our webinars take place once a month, and we hope to have another webinar in the coming months, also in this time zone. You may view the webinar recording in a couple of hours on the ISIS website. Please check the ISIS website and also our YouTube channel. As mentioned before, members, you please just log into your accounts, and then you have the archive of webinar presentations and recordings in the members area. If you have any comments or feedback, we welcome you to share this with us so that we can continue to improve our webinar service for you. Please participate in the survey or send your feedback to public.relations@isis.org. And that's it from me, that's it from all of us, wishing you a wonderful start to the day or evening, afternoon, whatever time it is in your part of the world. And I'm now going to close the webinar. Bye-bye.
Auf Wiedersehen.